So this type of question just needs to be considered in the same way that you might consider like having a block being attached to another block being pulled across a surface. And in that case, you know how the tension force is an internal force, and it points to the left on one block and to the right on another block. In the same way, as we look at this system, we are going to consider an internal force, but it is the force of static friction, which is really pushing one of the blocks forward and working against the motion of the other block. So this question is talking about two objects that move without slipping. So why that's going to be important is it does tell us to use static friction, but it also tells us that they have the same value of acceleration. And so we'll just use A to represent that acceleration. To understand this problem best, it's probably a good idea to draw some diagrams here. So let's start with the top block. The top block is being pulled forward by a force F in the picture. It would have its downward weight of m1g. And then there would be a normal force, we'll just call that F sub n1. Now there is actually another force on this, but I'm going to wait to talk about that in just a minute here. Let's go to the other picture. So my picture of M2, actually let me put it down here. My picture of M2, now there's nothing actually like from the outside pushing block 2 forward or backwards. But at this interface right here, there is going to be friction. And so there's a static frictional force that pulls that block forward. So that's our F sub F. And if you want to put S on there to remind you that it's static, you can do so. That force is our backward force on the top block. So we'll just call it the same thing, F sub S. All right. Now, there's no backward force on the 2 kilogram, or the M2. We're told to consider the bottom surface to be frictionless, so we don't need to worry about that. And this frictional force, it either points to the right or to the left. It can't be both. And so that is what pulls it forward. It would have its weight pulling down, m2g, and then it would have a normal force up. But there's also contact with this object from that block above. And so that this normal force, N1, is also going to be acting downward on this block here. Now that's not going to come into play really with this situation because there's no friction at the bottom. Because the only friction is at this interface, the only normal force that matters is the one that's at that point. And so that's going to be the Fn1, and that's going to correspond to m1g. All right, so how are we going to find this maximum value of force? Well, let's start by using F equals ma to write an equation that includes this net force that we're looking for, or this pulling force that we're looking for. So you could look at the whole system, or you could look at an individual object. I'm going to choose to look at the whole system, since the whole system, or with the whole system, I can ignore those frictional forces because they're internal forces for the whole system. That is what pulls the entire mass, m1 plus m2, at the same acceleration for everything. So now my goal is to figure out an expression for the acceleration. And so I can look at either one of these blocks. I'm going to choose to look at this block here, M2, just simply because it's a little bit simpler of a situation. All right. So again, this was written using the system, and I'm going to use F equals ma, and I am going to write another equation, but this time I'm going to look at M2. And for M2, the only force pulling forward is the frictional force. So I have my frictional force. That would equal M2 times A. Now friction, because it's static friction, I need to think about, am I at the point where the object is about to move or not? Is it just like the responsive frictional force. Well, I am at that maximum point because I'm trying to find the maximum value of pulling force, which would correspond to the maximum acceleration. And if I'm using, or I'm trying to determine the maximum acceleration, I would have to be using the maximum frictional force. So it does work out that I am going to be able to say that frictional force is mu sub s times my normal force. And my normal force in this case is, again, F sub n1, because the surface is below that object. All right, so this will allow me to find an expression for my, my maximum acceleration by saying A max is equal to mu sub s times, okay, so F sub n1 is going to balance out with m1g, and then that divided by m2 would give me an expression for my acceleration. And then it's just a matter of making sure that I state my final answer in terms of all the variables that are given. So my maximum value of pulling force would be m1 plus m2 times, and then I substitute in this expression that I just found. All right, so here we have a similar situation, except that we're pulling the bottom block instead. And so my pictures are going to be very similar to what I drew before. The difference here, though, is that the top block has no applied force to it, no outside or external force. The reason why the top block moves now is that static friction. Of course, I've got my weight and my normal force. And it's the bottom block that has the applied force, and it feels a leftward pointing frictional force. So these two forces here, this one and this one down here, these are the Newton's third law pairs, that if two pushes one forward due to friction, then one pushes two backward due to friction. And again, I would have my same weight forces. The normal force would correspond downward from the top block, and then there would be a different upward normal force at the bottom surface, which isn't going to really come into play again. All right, so now back to our calculations. We would write the same equation that we did before, that our force ends up being our total mass times our acceleration. I won't be quite as formal here. And again, if I'm looking for the maximum force, I need the maximum acceleration. And so the same sort of thing, I would now look at whichever one of these pictures seems to be a little simpler if I have the choice. So I'm going to pick the top picture now, and I can say that the force of friction would equal m1 times the acceleration. And again, of course, if I'm looking at these maximum points here, that's where I can use the actual static friction equality. So I can say mu sub s times the normal force, and I'm using this normal force. That's the frictional force I'm interested in, or what other normal force that affects the frictional force that I'm interested in. So m1g, and then that equals m1a max. Okay, but something different happens here because of the the switch of where the forces are and so forth. My mass actually cancels out. All right, and so my A max is just mu sub s times g. And so my maximum force would be m1 plus m2 times my acceleration. So I'm going to plug in that other expression, mu sub sg.